Hi, welcome to Sam's Math Lectures and Sam's Math Adventures, episode 2. So, what have I been up to this week? I've been working. I've been going to lectures, doing problem sheets, getting stuck into term. I don't really want to talk about any of that today. I've done lots of interesting things. I've done a lot of cosmology. I've spent lots of time working with path integrals, and there will probably be a video about path integrals, maybe even a series of videos about path integrals coming soon when I can get everything sorted out enough that I want to record it. I just need to go through, check that I'm happy with all the explanations. So that is likely coming soon. What I have done this week outside of sort of my degree is I acquired some books. They're pretty old-fashioned, hardbound, really nice books that I acquired from a friend. They are Lectures in Abstract Algebra by Nathan Jacobson, which was sort of what sparked my everything I'm going to go into today. So when I saw the name Jacobson, and I thought, actually, that sounds familiar, because in commutative algebra, so the theory of rings, commutative rings, there is something called the Jacobson Radical and the Jacobson Ring. And so I looked it up because Jacobson, it's a not a super common name, so I looked it up, and yeah, turns out it was these books, first written in 1952. These editions were printed in 1964, were written by Nathan Jacobson, which is interesting because he's not a household name mathematician. He's no Cauchy or Gauss or Euler, but he's still a big name in that maybe we don't remember him so much, but there are big things named after him, which is the first thing I'm going to get to talking about in a minute. In fact, yeah, let's go to that now. Okay, so what we need for this is we need a ring. So a ring, what this is like a generalization of, you could think about matrices, although we won't because we'll be talking about commutative rings. Polynomials form rings. Integers are probably my favorite example of a ring. So integers are, you can add them, you can subtract them, and you can multiply them. And you can do those with polynomials and matrices as well, and many other things. But these are sort of three of the big common examples. So a ring R plus times is a set R. So this is our set of numbers or objects with addition, and so that's plus, which is a binary operation. We take two elements of R and it gives us a third element of R, and multiplication. And so multiplication times R times R to R. Maybe this was a bad choice and I should instead call this dot. We will generally drop the dot anyway. We'll just write AB for A dot B, such that. So first of all, we want both of these to be associative. So for all A, B, C in R, A plus B plus C equals A plus B plus C, and AB times C is A times B times C. So that's good. It means we do not need brackets for a lot of what we do. So that's the first thing. Then we want addition to form an abelian group. So we want to be able to subtract, and we don't want order to matter. So first of all, we want there exists a 0 element in R, such that for all A in R, 0 plus A equals A. So we can add nothing. That's a good start. And for all A in R, there exists a minus A in R, such that A plus minus A. We're not thinking of the minus here as minus 1 times A. It will be minus 1 times A, but we're not speculating that right now. We're just saying there is an element such that when we add it to A, we get back to 0. So that tells us that R with addition is an abelian group. Then what else do we want? I think the only other thing we have to say now is that we have distributivity of multiplication over addition. So that means that for all A, B, C in R, basically we can multiply out brackets. A, B plus C is AB plus AC. So we just multiply each element inside the bracket. And A plus B, C is AC plus BC. So we have to do left and right differently because we haven't specified commutativity. And then other things. So we will also impose that there exists a unit, so we'll be working with unital rings. So there exists 1 in R, which does the normal thing that 1 does, which is that for any element in R, 1 times A is equal to A. So that's a unital ring. That's not strictly required, but generally required, and we're gonna require it. And then we're also going to require that for all A, B. Ooh, I missed out something very big here when I was talking about it's an abelian group, and I forgot to say that for all A, B in R, we need A plus B equals B plus A. Order of addition doesn't matter, because that's a very important property of addition. I mean, you'd think that that's an important property of multiplication as well, but matrices don't have that. Most of the rings we work with are commutative. I say most. Most of the rings you work with in a commutative algebra course are. So for all A, B in R, AB equals BA. So again, that's a sort of surplus requirement. And then some people say that 0 is not equal to 1. If 0 is equal to 1, then that means that every element ends up being equal to 0, because we can show that 0 times A is equal to 0, but 0 times A is equal to 1 times A if 0 equals 1, so that means that A is equal to 0 for all elements. We're not going to worry about that. The 0 ring is useful, ish, so we'll allow it. Okay. Now, this is a very, very crash course on rings. If we also had that for all A in R without 0, there exists A inverse in R such that A inverse equals 1, then we say that R is a field. So that's sort of, we have division. We don't always have that, so integers don't have division, polynomials don't have division, real numbers have division, or rational numbers have division, so they're a field, which is more structure than a ring. What we do have is something called an integral domain. So we'll ignore, R is not a field right now, R is just a commutative unital ring. If for all A and B in R, if A and B are not 0, then AB is not 0. So that means that we have no sort of divisors of 0. You can't take two things that aren't 0 and multiply them, get 0, which is not true in every ring. I will give some examples in a second. Then we say that R is a domain or an integral domain. Integral domain. Okay, so those are two special types of ring. Not every ring is, so if we take the ring of 2 by 2 real matrices, then I think 0, 1, 0, 0 times 0, 1, 0, 0. Is that going to be what I want? No, that's not it. I want this to be a 1, and I want this to be a 1. There we go. Now that times that is equal to, that's 0. We get zeros everywhere. So this is an example of a ring which is not an integral domain. Is 2 by 2 real matrices or matrices with integer entries, whatever, something like that. This is not supposed to be a lecture on rings, so I'm just flying through things without motivating anything, because I just want to talk about what a Jacobson ring is. Okay, so an ideal I in R is a subset I of R such that for all A and B in I, so for all elements in our ideal, A minus B is in I. So what we're saying is that also I is non-empty. Otherwise we'd have the empty set as an ideal, and we don't want that. I don't know if it causes problems. It might do. Basically what we're saying is it's an abelian subgroup of the addition abelian group of the ring. We're ignoring multiplication for now, but then we say that for all A in our ideal and for all other elements in the ring, anywhere in the ring, S times A is in our ideal. So that's stronger than being closed under multiplication. Obviously it is closed under multiplication because if S is in I, then S is in R. So the multiplication of two elements in the ideal will be in the ideal, but it's stronger than that. So an example is in the integers. N times Z, so this is 0 plus or minus n plus or minus 2n, basically the set of multiples of n. Let's fix n equals 2. Any integer times a multiple of 2 is a multiple of 2. And obviously we've got an abelian subgroup there because we add up two multiples of 2, we're going to get a multiple of 2. So that's an ideal. It's not a subring because it doesn't contain 1. If the ideal does contain 1, it has to be the full ring because we have this condition here. So if 1 is in I, then for all S in R, S times 1 is just S is in the ideal. So that means that the ideal is the whole ring. So generally they don't contain 1. Okay. Now the final construction we're going to need is the idea of a quotient ring. So let's do given an ideal I of R, then we can think of cosets in the same way as groups. So R in R, then R plus I is just the set of elements R plus I where I is in the ideal. So it's precisely our cosets in an abelian group sense. We're ignoring multiplication for that. And so we can take the quotient because R with addition is an abelian group, so every subgroup is normal, so we can always take the quotient, and we can define R plus I plus S plus I is just R plus S plus I. That makes sense because we get elements R plus I plus elements S plus I primed, but then that's R plus S plus I plus I primed, but that's also an I because I is a subgroup of addition under addition, so we get R plus S plus I. And then we also have R plus I times S plus I equals RS plus I, and that's because we have R plus I, S plus I primed, so now we can distribute out because we've got distributivity, so we get RS, then we get IS, well that belongs to I because we've got that extended closure under multiplication. We've got RI primed, that's also in it because we have a commutative ring. If we had a non-commutative ring, we'd have to specify that we have a two-sided ideal, which basically means that we also add on that AS is also in I. Otherwise, if we just have this is a left-handed ideal, or a left-sided ideal, this is a right-sided ideal. They're exactly the same in a commutative setting. In a non-commutative setting, they're different, but we don't care about that right now. And then if it's both, it's two-sided. So then that's in I plus I primed, which is also in I. So this whole thing is in I, so we get RS plus I. And so that means we have a quotient ring, because we have a new ring where we've gotten rid of that, and R over I, which is a quotient ring because it is a ring, and we have a natural map from R to that, where we basically take R to R plus I, and in that setting I maps to 0. Any element of I, maybe I should write I in I maps to 0, which is what we want. I haven't spoken about what ring homomorphism is. This isn't a course on rings, so we're going to ignore that. Okay, so then what next? We're going to talk about types of ideals. We're nearly at the idea of a Jacobson ring, I promise. And I'll be talking about physics, which is way more interesting, probably for most people. So we have that I in R is prime. So this is an ideal is prime if R over I is an integral domain, an ID, which that's great, but that's not very clear. This is sort of a very abstract way of saying it, but that means that if R plus I, S plus I equals 0 plus I, well that's if and only if RS is in the ideal. Well, if R over I is an integral domain, then that's saying that RS is in I if and only if one of R or S is in I. Could be both of them. So if you multiply two things and you end up in the ideal, then one of them must have already been in the ideal. And so an example of this is the even numbers again, 2z. Because if we take n times m is in 2z, well that means that n times m is even. And that means that at least one of n and m was even from the start, right? And the same with 3z. If n times m is a multiple of 3, well that factor of 3 must have gotten in there somewhere, so one of them at least was a multiple of 3. And in general, pz is a pz is, what do you call it? Pz is a prime ideal for any prime number p, because if you multiply two things and they end up being a multiple of the prime number, well, the prime number doesn't have any factors, so we can't get that out of nowhere. So at least one of those two numbers was already a multiple of p. So that's a prime ideal. I is maximal, a maximal ideal, if R over I is a field. Now that's strange. Not strange, but it's not clear, right? So we need to work out what that means. So a field only has two ideals. It has the zero ideal that contains precisely zero, because 0 plus 0 is 0, and 0 times any number is 0. And then it has the whole ring, because we have inverses, right? If K is a field, and I is in K, and R not equal to 0 is in I, then for all S in K, SR inverse is in K times R must be in I, but that's just S, so the ideal is the whole field. So ideals only have those. And so another important fact from ring theory that we're going to skip over is that the ideals of R over I are in one-to-one correspondence with ideals of R containing I. And containing doesn't have to be proper in this sense. And so that means that the only ideals here are 0, which corresponds to I itself, right? I is an ideal that contains itself. It's the smallest ideal that contains itself, so it must correspond to the smallest of the ideals of the field. The correspondence is order preserving. And R over I must correspond to R, because again we've got the largest ideal that can contain I is the whole ring, and the largest ideal of the field is the whole field, so those two must correspond. And so that means we cannot have anything that slots in the middle here. So there does not exist an ideal J of R such that I is contained in but not equal to J, which is contained in but not equal to R. So we have a maximal ideal as an ideal which is not properly contained within another ideal that is not the whole ring. We have to say that is not the whole ring because we want to make sure that the whole ring is not maximal. And the reason for that is that R over R is 0, which is kind of a field, but we don't want it to be a field. We say it's not a field because it's like I don't know, mathematicians don't like it. Normally we love zero objects, not fields. No zero fields allowed. Okay, wow, we are nearly there. So next we have that the radical of I it's the set of all elements in R such that for some power n greater than 0, x to the n is in I. So not elements that multiply into I directly, but you raise it to enough powers, then you end up in I. So where does this come from? Let's talk about it properly. So the nil radical of R is basically the nilpotent elements, so elements which when raised to a power will become 0. So x in R such that there exists n greater than 0 such that x to the n equals 0 in R. So can I think of an element off the top of my head? Certain matrices will square to 0. Don't ask me which ones, I can't remember. But it happens. It does happen. Because otherwise we wouldn't be able to get radicals. Of course. So if we take the ring Z mod 4, so that is 0, 1, 2, 3, and it has addition and multiplication modulo 4, then 2 times 2 is 2 squared, which is 4, which is 0. So 2 squares to 0. In Z8, 2 cubed is 0. Okay, so here's some examples of nilpotent elements. And so we call this, we write it as square root I, is this, and we actually have the square root of I is in one-to-one correspondence with the nil radical of R over I. And why is that? Well, if x to the n is in I, well, that means that x plus I to the n equals 0 plus I. That's not a one-to-one correspondence, that's an if and only if. So, not really one-to-one correspondence, but it is a correspondence. It's the pre-image of, I think. And I've lost my pen, there we go. But there is a correspondence it comes from. It's the pre-image of the nil radical, I think, after that projection map. Okay, so that's the radical. And we can actually say that, I'm not going to prove this because I can't remember the proof off the top of my head, that I over I is equal to the intersection of P in spec R, and so this is all prime ideals of R, P of spec R, such that I is contained in P of all of those. So basically we take every prime ideal containing I, we intersect them, we're going to get another prime ideal, and we end up with the radical of I. Yep, that was a radical. Now, what do we do next? Let's give an example of a radical. So 8z is contained within 2z, and that's the only prime idea that's contained within. So the radical of the multiples of 8, so any number which when raised to some power can become a multiple of 8, had to have been a multiple of 2 to start with. The radical of 6z is 2z intersect 3z. It's actually not very interesting in the integers, because what is a multiple of 2 and a multiple of 3? That's just 6z. I think if you chose 12z, then you end up with 6z as well. So basically, if we have p1 to the n1, p2 to the n2, pk to the nk, so we form a number by taking k prime numbers, raising all to a power. We take multiples of that, we take the radical of that, then it's p1, p2, up to pk, multiples of all of its prime factors. I think I'm actually going to have to publish 2 parts to this video because this is going on for a lot longer than I thought. Okay, so that's what the radical of an ideal is. Then next we have, well, the nil radical is actually the radical of 0 now, which means it's the intersection of all prime ideals, right? Because we know that this is true because this is things which when raised to a power are 0, and this is things which when raised to a power are in the 0 ideal, which is 0. Same thing. And so that must be, by our theorem that I did not prove, intersection of just all the prime ideals, because all of them have to contain 0. Then we have that the Jacobson radical, here we go, of a ring R. It doesn't have a nice meaning like the nil radical does, but it's integral of SPM is the maximal spectrum, so all maximal ideals of R. Done. And then we also have the Jacobson radical of an ideal, and it's exactly the same. It's the pre-image of the Jacobson radical of R over I, or just M in spum R such that I is contained in M of M. So intersection of all maximal ideals containing I. There is a theorem that says that there is always such an ideal. It uses Zorn's lemma, and we can also say that there is always a prime ideal containing I, because every maximal ideal is prime, and you can see that because a field is an integral domain. So if R over I is a field, which means that I is maximal, then R over I is integral domain, which means that I is a prime. It's a very abstract proof, but it's easier than trying to prove it directly using the sort of easier, more common sense definitions of what those things are. Okay, so that is a Jacobson radical, and a Jacobson ring is if for all I in R, the Jacobson of I is equal to the radical of I, then R is Jacobson. Why do we care about this? Well, it means that, in particular, for any prime in the spectrum, we have that P is its own radical, because it is the smallest prime ideal containing itself, and then is the intersection, of M in spum R, which contain it, of M. So every prime ideal is the intersection of maximal ideals in a Jacobson ring. Now, what we like about that is when we do algebraic geometry, we end up talking about prime ideals and maximal ideals, and it's much easier to work with maximal ideals because maximal ideals of polynomial rings corresponds to points in affine varieties. I'm not going to go into detail, but basically we like working with maximal ideals, and so the fact that every prime can be written as an intersection of maximal ideals is good. It's something that we like. And then other good things about the Jacobson property are that any finitely generated algebra of Jacobson rings is itself Jacobson. So if we have basically k of x polynomials with coefficients in a field k is Jacobson if k is algebraically closed, because the prime ideals are precisely linear polynomials. Are x minus a, for A and K. And yep, but those are also the maximal ideals. So prime ideals are maximal ideals for an algebraically closed field K. But that means that any algebra over this, which, so first of all, that includes, maybe we'll use the fact that K, there are no primes, there are no maximal ideals, or there are two prime. The prime is 0, the maximal ideal is 0. They are equal, because the K itself is neither maximal nor prime because it's the full ring. And so that means that K is Jacobson for any field K, and so any algebra x1 to xk divided by any ideal of that algebra, which is going to correspond to a coordinate ring, is Jacobson. So we have this nice prime maximal correspondence. That's why Jacobson rings are useful. I'm gonna keep going in another video.